Hello, welcome back to the class where we are talking about your Nast equation, how the Nast equation can also be useful for the derivation of the different E0 values and the E values rather. So, we will be talking something in terms of the precipitation reaction what we have just now seen in our previous class, that means the precipitates and the complex ion formation we will see. So, complex ions if they are developed or generated into the medium. So, we will see again without complex making complications for different other species. We will stick on the same species which is silver ion, because we also know by this time that what are the different values of these potentials. So, the silver electrode, because we will be looking for and we are approaching towards in that situation where we get that corresponding generation of the silver electrodes, the different types of silver electrodes we can have. So, the species what is being involved can be silver ion itself, silver chloride, then silver iodide, and we will take the help of some species for these complex ions what can be formed, as we all know that this can be with thiosulfate anions S2O3 2 minus. So, its charge is 2 minus for the thiosulfate anion. So, overall charge will be 3 minus for the silver ion in the +1 oxidation state. So, when this we have, so when it accepts one electron, we get that silver as the solid separating out from the medium, and we also know the corresponding standard electrode potential value for that, which is E0 for Ag plus Ag is equal to 0 point plus definitely 799 volt. So, close to 0.8 volt for that corresponding reduction potential of silver ion, and we all know that this particular silver, this is the silver ion which is accepting electrons. So, it is a very good oxidizing agent, because the positive values of the potential we know with respect to the standard hydrogen electrode, we can measure this, and it is the corresponding oxidizing agent which will be above the corresponding level from what we know, that is above your hydrogen, and the below we have the reducing agents. Then just now what we have seen, the solid silver chloride is accepting electron, giving rise to your silver as solid and the chloride ions. So, this we can have, and the E0 for this will be written as the corresponding silver chloride silver, but this how do we know what should be the value of these? As we have seen, this value is known, but some manipulation of this particular equilibrium we are getting something, that means instead of this we are handling something where silver solid can react with the chloride ion giving you silver chloride and electrode, or in a different way that silver chloride solid is reacting with electron from the electrode for its reduction to solid silver and the chloride ion. So, how do we know this particular magnitude of E0 value? Similarly, the solid silver iodide we know that is the corresponding analytical test for the silver ion. When we add chloride or when we add iodide, it is getting precipitated as the corresponding silver iodide as the salt. So, in the same fashion it can also give that silver solid and the iodide ion, and here this E0 value also is for silver iodide and silver electrode. That means you have the saturated of this and the wire give rise to the corresponding half cell, but this also we should know for calculating it out. Similarly, this when accepts electron, what we get over there. So, that the reduction reaction again, because the formation of this silver, metallic silver, that means solid silver from the silver ion is so vast that it can directly get from the corresponding silver ion, or we can get it from the corresponding silver chloride concentration in the solid form, and we get that as the corresponding thiosulfate ion as the corresponding species, what is being generated as again solid silver, and the release of the corresponding 2 number of thiosulfate anion H2O3 2 minus. And we have therefore the corresponding E values for E0 of this silver H2O3 whole 2 3 minus against silver, we should know this value also. So, how do we calculate or how do we find out all these values, that is important, and what we find that in this particular case, that manipulating all these values for these situations, we should take the use of the corresponding E values again. So, this particular case, if we consider the corresponding E0 values for silver ion to silver thing, then as we have seen earlier, that is 0.0592 divided by 1 and log of 1 by the corresponding silver ion concentration. So, if we move from there, that means the reduction of silver ion to silver formation, it gives us to that particular value, but when it is giving you the corresponding silver chloride precipitation, that means what we are looking for? We are looking for the corresponding E0 value for silver chloride and silver electrode, which is different. So, what are the things can be introduced for this is therefore that we have to use this particular silver ion, but we should get that silver ion concentration in terms of the corresponding precipitated form of silver chloride. That means, this will be equivalent to that of your solubility product constant value, the Ksp value. We all know that the Ksp value is nothing but your product of the concentration of the silver ion and that of your chloride ion concentration. So, this silver ion concentration will be equal to your Ksp value divided by the concentration of your chloride ion. So, what we get, the corresponding E0 value for this will be equal to therefore your E0 for silver ion to silver, which is all these cases are same. Then if we change the corresponding sign of these, that means it will be plus of 0.0592, then log of Ksp, that means your this value. So, your thing will go like this, that means the log of Ksp value. So, log of Ksp value minus your 0.0592 of log of Cl minus concentration. So, that basically gives us the corresponding thing that you have this, that means silver ion concentration will be equal to the silver, that Ksp divided by this thing. So, your sign is changing to that means the plus value of this. So, what we get now is that your Ksp value, if you use, so this Ksp value is known for your silver chloride formation. So, the magnitude of this Ksp value, if we put that particular value and the value for this also, this is known to us, which is plus 0.799 volt, and we put this value also as 1.82 into 10 to the power minus 10. So, these are the requirements for calculating this to you. So, this will basically give rise to the corresponding Ksp value. That means, you should know about these things. So, if this is your unknown quantity, then we can find out the solubility product also, because it has some direct relationship for the concentration of the silver ion for its corresponding solubility product. And we all know that all these sparingly soluble salts, when they are undergoing some electron transfer reaction from these salts, we get this as an interconnecting thing for your Ksp value and the chloride concentration. So, this particular one will give you the corresponding chloride ion concentration, but on standard condition, because we are looking for this is standard electrode potential for your silver chloride silver situation. So, what should be the corresponding chloride ion concentration? The chloride ion concentration is nothing but by definition, then the standard condition its activity should be equal to 0, 1.00. So, it is by definition for your standard situation or the standard condition. So, for the standard condition, what you have, your Cl value is 1. So, that will, because this particular magnitude will be therefore equal to 0. We put these Ksp values, and when we put this particular value and multiply with this, we get some value which will be equal to your E0 for silver chloride silver case is equal to plus 0.799 volt plus minus 0.577 minus this 0.000. So, in a standard situation, what we get in this particular standard situation, we have this. So, that means this is the correction what we get by moving from a electrode which is silver ion to silver electrode to silver chloride to silver electrode. What we get is therefore that is basically this particular amount of change. So, it will be equal to 0.222 volt. So, what we are talking earlier in our previous transparency of the slide, what we see that this is now known to us. That means, it will be plus 0.222 volt. So, from here we can go there, that we can calculate it out for is. Similarly, now you know that what you should know, as we are looking for the corresponding Ksp value of silver chloride, which is there. So, we introduce in the Nernst equation the parameter what we are introducing is your Ksp value. Similarly, another Ksp value which is different from that of your silver chloride will be used for this. But how? So, that after getting all these values and calculations, we get these values. So, we should know the value, and the value is quite different, which will be minus 0.151 volt. So, you see the situation is because the variation from this. So, you have the value which is pretty high, close to 0.8 volt, then we go down, further for your silver iodide concentration and its solubility product. Then what about this? Because this will be the typical complex ion formation. So, what is this? This is your complexing agent. So, how you use this particular complexing agent, which is complexing these, and you have the concentration, that means this particular one. So, how strongly like that of your this insoluble precipitate, but this is not your insoluble precipitate, but you add some complexing agent. Sometime we consider this complexing agent as the ligands. So, when you add these complexing agents to trap the silver ion, so the relative concentration of these species are different from that of your free silver ion. So, that we should know, and how you know this E0 value. In this particular one, it is still for the less with respect to, but in the positive direction it is plus 0.017 volt. So, how do we calculate it out? How do we calculate this particular value of 0.017? That we will see, because already we know the trick that you have to use something that where it is directly related to the corresponding concentration, or if it is there, that means the corresponding concentration of these things, that means related to your silver ion concentration and these things, because this is for this electron transfer we are getting this, but otherwise the direct complexation reaction what is different from that, where the silver ions are available, which is reacting with 2 of the thiosulfate ion, giving rise to the corresponding complex species Ag S2O3 whole 2 3 minus. So, this is the corresponding complexation reaction from silver ion, because all these cases we are looking for silver ion, whether it is present as a free silver ion, or it is present with silver chloride, or it is present with silver iodide, or it is in the complex form. So, this concentration we should know. So, this is during the complex formation. So, this complexation we get that as the corresponding formation constant, formation of the complex. So, the corresponding formation constant what we have in our hand, and that particular formation constant is nothing but the ratio of the concentration of the complex form and the free ion form. That means, the product of the concentration of the silver ion as well as the product of the complexing agent. So, all these things can give rise, and if we consider that 2 of these are attaching to the silver ion. So, it is not in a very straightaway fashion. So, if we consider that the corresponding silver chloride we have these, and silver we all know that it can have a low coordination number, that means coordination number of 2. So, if we are trying to fulfill a coordination number of 2, and if we see that the silver is binding this one first, then in the second step you get the corresponding second one. The first one is binding to silver from this side, or the second one is binding to this particular silver from the other side. So, what we get that the corresponding formation constant for these and the overall formation constant is considered in as the beta 2. If we have a step K1 for the first attachment and K2 for the second attachment, we should get these as the corresponding beta 2 is the overall formation constant for the complex ion what is being formed. So, this particular one, so beta 2 is nothing but the ratio of these divided by the product of the concentration of the silver ion and the thiosulfate ion. So, like the use of your Ksp value, we now use the corresponding beta 2 value now during the complexation formation to evaluate out this particular magnitude of the potential, which is 0.017 volt. So, like this we have utilized this for the calculation in case of your silver chloride thing. So, now we will see that how directly we get that particular value for your complex formation. So, what we get? We get the corresponding E0 value definitely in the standard condition for the complex species is your Ag S2O3 whole to 3 minus, and the silver 0 is equal to your E0 Ag plus Ag. All the cases we will consider the corresponding standard electrode potential for the standard condition, because we are talking all in terms of the corresponding silver ion concentration, whether it is in the free state or in the complex state. And like that of your chloride thing, so it directly we will write now the thing is 50592 and log of your beta 2, the formation constant value. So, when we put this particular concentration at the concentration of these two values, that means these are the like your corresponding solubility product values in a tabular form. We get this from the data table, we get the corresponding beta 2 value for the silver thiosulfate complex. So, the formation constant, the beta 2 is your formation constant, which is nothing but the ratio of your silver in complex form. This is the species what is formed by this concentration of the silver ion and the concentration of the thiosulfate ion 2 times. So, this particular thing, so something we are relating now not in terms of your Ksp value, but now we are relating something for the complex equilibria, the metal ion complex equilibria. So, the metal ion complex equilibria that we all know that the formation constant, in some other way we can find out this formation constant. Now, the analytical chemist had that particular opportunity that he or she can use this thing in a nicer way, that if the potentials are known and if you frame the cell by taking the help of your standard hydrogen electrode or any other electrode, or you know the corresponding values for these, you can find out any unknown formation constant of the complex species. So, it is not that it is the thiosulfate ion. So, any other ligating group can also be helpful to determine this particular value. So, what we get putting these values, what we useful for that, and that particular one will then equal to plus 0.017 volt. So, that gives us a very useful information that when you have this magnitude of this E0 silver ion and silver potential is equal to plus 0.779 volt. So, you see, due to complex formation, what is our basic intention, that you try to reduce the free ion concentration, that means the silver ion concentration in the medium to a lesser extent. So, the complexation can reduce the corresponding potential value from 0.779 volt to 0.017 volt. So, that is the good information that what we can have for knowing these things, how complexation can help us for any reaction. So, how complexation is useful for any titrations, particularly the redox titrations and all other things, because one more important thing what we will now talk about in terms of another definition for discussing about the formal potentials. We will define this as what is that formal potential, but at the same time what we are looking at, as the silver is binding to thiosulfate and we all know the electron transfer for the ferric ion or the ferrous ion. Now, we will put some other strongly bound complexing agent such as cyanide ions. So, these cyanide ions are attaching to that. So, it is the corresponding ferricyanide ion FeCN whole 6 3 minus, and formation of these species, how they are changing, whether the corresponding electron transfer reaction will take place at the same potential close to that of your 0.77 volt, which we know for your reduction for ferric ion to the ferrous ion, or it is different, and how this complexation can change or manipulate the corresponding potential value. And we will see the corresponding value for this is therefore changing, and this particular change is due to that corresponding complexation reaction. So, how we define this particular formal potential? So, these are some empirical values. So, these empirically derived potential values. So, which compensate the types of activity and compensating the equilibrium effect. So, the types of activity in the reaction medium that we are adding cyanide ion and the equilibrium effect, these two things if we consider together, we can get the thing, that means the corresponding reduction of these as one electron transfer for these, giving rise to the ferrocyanide ion, which is FeCN whole 6 4 minus. And interestingly, for this particular case, we will find this as the corresponding value of E0 for is 0.36 volt. So, that is why it is very interesting to understand, and because it is not so high that of your ferric ferrous system. So, this particular value of this 0.36 volt will be useful to know us that this can change the value, and you can get this for as a standard material, because the corresponding potassium ferrocyanide or the sodium ferrocyanide, we all know that all these salts, that the ferro and ferricyanides are known. But if we can consider these corresponding salts as the corresponding NR4 salt, that means tetraalkyl ammonium salts, which can be soluble in some non-aqueous solvent like MECN or any other thing, and this particular value is a very standard one. Experimentally we can determine by some other technique, electrochemical technique. Experimentally we determine that. We will see in the latter part of these classes of electrochemical methods of analysis, which is useful for measuring the cyclic voltammetric analysis. So, is a standard sample for knowing the corresponding standard potential values for these cyclic voltammetric measurements. So, right now what we see that this particular value and how we can change or how we can manipulate the corresponding values in terms of the values what we require for electron transfer in a medium which is slightly acidic or strongly acidic. So, this value, that means the potential is plus 0.36 volt, and whether we can push it to a lower value or whether we can push up to another value, that we will see that this can be pushed to a value of plus 0.72 volt in 1 molar perchloric acid or sulfuric acid. But now interestingly what you can see or what you can find out is that in this particular case your values for all these, that means you are supplying H plus and ClO4 minus, 2 of H plus and SO4 2 minus, and earlier we are talking about the complexing capability of the perchlorate ion and the sulfate ion to the iron side. But now these values we are talking about the corresponding ferrocyanide and ferricyanide ions. So, there is no chance of decreasing the concentration by complexation with these anions. So, what we can see here now, that in these cases what we get, that the protonation at these values in at the 1 molar or the higher, at high proton concentration, we get the corresponding protonated form of these species, which is H3FeCN whole 6, which is ferricyanide, and ferrocyanide is H4FeCN whole 6, which is 2. So, this particular one, then the corresponding acidity of all these is important, and if they are there, that means the corresponding thing is that when the charge is less, then it is ferrous ion is weaker acid than your ferric counterpart. So, if they are strong and weak, therefore, the concentration of the free ions in the solution, the ratio of the species, that means the two species involved, that means your FeCN whole 6 4 minus concentration, that means this concentration divided by, this is the reduced form, by FeCN whole 6 3 minus the other concentration. So, if this is the thing, so that means you have the corresponding one, that means the ratio is changing. So, by this, that means in high concentration you have the corresponding change in the corresponding ratios of these two. So, in the Nernst equation, as I told you that what we are talking about, the corresponding magnitude, what should be greater than 1 or less than 1. So, this is less than 1. So, when it is less than 1, we get something or we get the information. So, their reactions is that the corresponding observed potential. So, that is why these observed potentials are going off. So, due to this particular manipulation in the acidic medium, the observed potentials are greater. So, that way the formal potential values are useful, and we can use all these things to understand something where we can see or we can know for our ultimate results will be your redox titrations. And during those titrations, because we all know that the titrations are the corresponding continuous process where the analyte is examined by the corresponding titrant what we add for analyzing the species. So, either the oxidizing agent or the reducing agent you can add to get these particular type of titration reactions. And one such example, and we will see that where we can titrate this, as I told you earlier that this ferrous ion can be titrated nicely from your school or college days. We determined that also by using the corresponding solutions of permanganate ion or the corresponding solutions of dichromate ion. So, these permanganate and dichromate ion concentrations were useful to manipulate these things, but another one is also very much interesting is the corresponding steric ions. So, steric ions are further strong oxidizing agent containing one single metal ion, because these are the corresponding oxoanionic species, because this has some thing to play, because it has the very unstable O2 minus present in it. So, it will have some affinity, that means the pH dependence. That means it will always attract the protons, and you have the formation of the corresponding water molecules out of that, and definitely this will be therefore the dependency there and the pH of the stability of these species. But in a particular reaction concentration that you can directly react or study this reaction for the steric ion, that means the tetravalent cerium with that of your ferrous ion to convert it to the ferric ion as well as the corresponding ferrous ion. So, in our next class we will be considering these as getting the corresponding redox titration curves and how we plot those curves to get those informations related to those redox titrations. Thank you very much.